Welcome back. We are now looking at Chapter 12, Section 2. Chapter 12, Section 2 asks us to focus on certain terminologies and gives us two different kinds of examples, and I'm going to look at both of them. The first example deals with a deck of cards, but some of the terminologies I just want to review are what is going on when we draw a card from a deck of cards, or when we roll dice, or when we look at a coin that is flipped. These are random experiments. When we do those, not that we do them all the time, we sort of, I guess, think about them more. We can say that when something satisfies our condition, it is an outcome. And probability is the fraction of the number of outcomes in the event over the number of outcomes in the sample space. Now, what is a sample space? The sample space is the set of all outcomes. So when we had the example of rolling dice, there were 36 outcomes in the sample space. You could get a 1 and a 1, or a 1 and a 2, or 1 and a 3. Okay, and they were all enumerated on page 632. That is your sample space. Okay, so there are some terms that we need, and then this idea of probability is the fraction of the number of outcomes in the event and the number of outcomes in the sample space, which is your total, and you make that fraction. If the number of outcomes in the event is equal to the number of outcomes in the sample space, in other words, all of the events are your sample space, then your probability is a 1, which means it's guaranteed to happen. And if there are no outcomes in your sample space that satisfy the condition, then you get a 0, which is this event can never happen. So never happening is 0, always happening is 1, and probabilities in between are a fraction between 0 and 1, formed by the ratio of number of outcomes in the event to number of outcomes in your sample space. In example number 1 on page 635, they talk about a 52-card deck. I don't want to assume that everybody knows what's in a 52-card deck, so I'm briefly going to review what is found in a 52-card deck. You may want to go retrieve a 52-card deck somewhere and take a look at it if you haven't already played with a 52-card deck a little bit. For our purposes, we are just using them in terms of a probability or counting experiment. In a 52-card deck, we have 4 suits. The suits are diamond, heart, and diamond and hearts are red, clubs, and spades. And clubs and spades are black. Clubs look like it's kind of like a clover, and a spade looks, I guess, kind of like a shovel. And they are black. So half the deck is red and half the deck is black. 1/4 of the deck is diamonds and 1/4 of the deck is clubs, and each suit is 1/4 of the deck. Within each suit, we have ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this goes up to 10. And then after 10, we have 3 more cards, jack, queen, and king. And jack, queen, and king are considered face cards because they have a face on them of a jack or a queen or a king. They usually have a J or a Q or a K and then a face in between. Okay, so with that in mind, let's take a look at question number 1 on page 635. It has a lot of parts to it. So, a card is drawn at random. Now, what does that mean? You know that when you buy a deck of cards, they are in order of from ace to king for each of these suits. So if I were to draw a card from there, I might think that may not be at random because I already know the order of the cards. So I might try to count them and say, well, I'm going to try and get the ace of spades, so I know where it is. Here it is. So that is not random. In order for it to be random, we must shuffle the cards many times to get a huge combination of, there are many, many millions, gazillions of ways a deck of cards can be shuffled. And once we have done that with some, regularity and skill, we know that any card I pick out of there is random because I don't know what order the cards are in. So, number 1A says, if a card is drawn at random from a normal 52 card deck, what name is given to the act of drawing the card? That is a random experiment. B. How many outcomes are there in the sample space? Well, that just means if I were to randomly pick any of these objects, how many different outcomes are there? And every card is different, although they sometimes share a color, or they share a number, or they share a suit. Each one is different, so there are in fact 52 outcomes in this random experiment. C. How many outcomes are there in the event? Now we're just counting, right? This is not a probability question yet. How many outcomes are there in the event the card is a face card? So remember we said there are 3 face cards in 4 suits. So there's 3, 6, 9, 12 face cards. 3 of each suit. D. Calculate now. Here's a P. See that P? That means the probability of the card is a face card. The card is a face card. So here's where I take the number of outcomes in the event and put it over the number of outcomes in the sample space. So that would be 12 over 52, which reduces, divide each by 4, is 3 over 13. E. Calculate the probability of the card is black. So I mix up the cards, I reach in. What's the probability I pick a black card? Well, half the deck is black. So, or if I put all the numbers, 26, each one has 13. I probably should have said that. Each one of these has 13, right? Ace through 10. Ace is like a 1. Oh, I have a mistake here. I put a 1 here. There is no 1. Ace is the 1. Ace 2, 3, 4, so on. Okay, so I apologize. I made that incorrectly. I had ace, then 1, 2, 3. It goes ace, 2, 3, and so on. So there are 13 cards in each suit. So there are 26 black cards out of 52, which is half the deck. F. What is the probability? Sorry, I got to turn the page. I think it's an ace. Yeah. Calculate the probability that I get an ace. There are 4 aces. So my outcomes, number of outcomes is 4. My sample space is 52. That is then 1/13 of both of those divided by 4. G. Calculate the probability the card is between 3 and 7. Okay, the probability the card is between 3 and 7. Does it say inclusive? Yes, it does. So we're going to include 3 and 7. So I'm including 3 and 7, so it could be 3 or 4 or 5 or 6 or 7. That's 5 cards. 5 cards satisfy 3 to 7 inclusive. In 4 different suits, there is a 3 through 7. So that's 4 times 5. There are 20 cards that are 3 through 7 inclusive. Right? There are 3 through 7 is 5 cards in 4 suits. So that's 20. Let's reduce that, divide both by 4. We get 5 out of 13. 5/13 are the numbers 3 through 7 inclusive. H. Calculate the probability the card is the 8 of clubs. So H, the card is the 8 of clubs. That's one card. That's a very specific card. There's only one of them in here. Here's my clubs, and there's an 8. So that's 1 out of 52 for H. I. I asks us to find the probability that the card belongs to the deck. Oh, that's nice and easy. I like ones like this. Card is the deck. Card belongs to deck. Well, probability if I pick a card out of the deck of cards that it belongs to the deck, all of them do. All 52 of them do. All 52 cards belong to the deck, so that's a 1. So 52 out of 52 is 1. That is guaranteed to happen. It is assured that if I pick a card out of the deck, it will belong to the deck. So that probability is a 1. And I'll put J down here. J says, what is the probability that the card is a joker? Ha. Now, they may be trying to fool us because some of us know that when we buy a deck of cards, there are 2 jokers in there. And that's so that they give you an extra pair of cards in case somebody loses one or the dog chews on one, and then everybody knows that the chewed card is the ace of spades. So we can replace it with a joker that looks just like all the other cards on the backside so that our opponents don't know what we have in our poker hand or gin rummy hand or whatever it is we're playing. And we can just cross out the joker part and make it the card that we chewed or lost or got jelly on or whatever it is. So there are 2 jokers in the package when you buy it, but they are not considered part of the deck. The deck is made up of 52 cards that have these qualities, the suits and the numbers ace through king, and they do not include the jokers. So jokers are not in the deck. So if I take a deck of cards and I shuffle them and I say, what's the probability I'm going to pick a joker? Well, there are no jokers in there. So it is 0. The probability of joker is 0. There aren't any jokers in a deck of cards. Okay, let's move on and take a look at number 2. I want to look at this together because it involves a different sample space. So example 2 involves a penny, a nickel, and a dime. So we have a penny, a nickel, and a dime that are tossed. These are not weighted, they are fair. So it is equally likely that the head will appear as much as the tail. Let me be clear. If you actually flipped the coin 100 times, you may not get 50 times head and 50 times tail. But if you did it over many, many thousands, it would be very close to 50. And also, the experimental may be different from the this calculated. There's another word for this. It's escaping me right now. Sorry. But this is the theoretical probability. So we have a penny, nickel, and dime that are flipped at the same time. Each coin can come out either heads or tails. Okay, so either heads or tails, heads or tails, heads or tails. Okay, and so we're now going to answer 2A, which says, what is the name given to the act of flipping the coins? This is a random experiment. To B, there are 8 elements in the sample space. That's nice that they told us that. For example, HHH, THT, and so forth. List all 8 outcomes. Great. Well, I've got 2 of them here, all heads and all tails. But suppose we take off this for a second. We know we're going to get to the all tails. So we can start with all 3 of them being heads, right? Let's insert 1 tail. So what about heads, heads, tail, heads, tail, heads, or tail, heads, heads? Let's make it so there are 2 tails. Heads, tail, 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 heads, tail, 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 heads. So I sort of moved the H through there. And then the last one would be that they are all tails. So this is every combination, every permutation of getting flipping a penny, nickel, and dime. You could get all heads, or 1 tail in these 3 combinations, or 2 tails in these 3 combinations, or no tails. And altogether, there are 8 possible outcomes. And that also makes sense because it's 2 to the third, right? 2 times 2 times 2, which is there are 8. So, but this is our sample space. These are all of the possible outcomes of flipping 3 coins, a penny, a dime, and a nickel. So B comes back and says, to answer this question, list all 8 outcomes. Here they are. And, and that's it. Okay, so C, let's change this to C. So this technically qualifies as B. Excuse me. How many outcomes, so we're counting, how many outcomes are there in the event exactly 2 of the coins are heads? The notation for this is to put an N out here and exactly 2 heads. So the number of outcomes of exactly 2 heads, which is different from the probability, right? The probability is a fraction. This is just counting number of outcomes of exactly 2 heads. Okay, so in this first outcome, there are 3 heads. That is not exactly 2 heads. Second outcome, there's 2 heads, there's 2 heads, there's 2 heads, and then the rest of these do not have exactly 2 heads. So there are 3 out of 8 that have exactly 2 heads. Okay, what about D? D says, now we're calculating a probability because I see the P in front of the parentheses. Calculate the probability of head, head, tail. Well, in looking at my list here, here it is, right here, head, head, tail. There is only 1 in my entire sample space. So 1 out of 8 is head, head, tail. Order matters here, right? Because it's a penny, nickel, and dime. That order is important. It's different if I change that. Okay, E, calculate the probability of exactly 2 heads. Now, I already know, I made a mistake in C, didn't I? Here I said I'm only counting. So this should just be 3. Excuse me, I was like, didn't we just do that? But look at what I did. See, this is just counting. How many are 2 heads? There are 3. That is the answer to C, so I apologize. Go back and fix that. It should be just 3. And then E is the probability of exactly 2 heads, which is 3 out of 8. Okay, I jumped ahead of myself there. So please notice the difference between just the number of exactly 2 heads, which is 3, and the probability of exactly 2 heads, which is 3 out of 8, which is now making it a fraction. Jumped right into that one. F, calculate the probability of at least 2 heads. Probability of, at least 2 heads. That's 2 or more heads, right? So this is a probability, so I already know I have a denominator of 8. All right, so at least 2 heads would be here, 3 heads, yep. 1, 2, 3, 4, not 2 heads, so 4 out of 8. 1/2. G. G asks us to calculate the probability that the penny and nickel are tails. Probability that the penny is a tail and the nickel is a tail. Probability, so my denominator is 8. I already know that. So here, the penny is a tail and the nickel. Let me just read that again. And the nickel. Penny and nickel are tails. So they both have to be tails. That would be here and here. There they're both tails, and there they're both tails. So there are 2, which is 1/4. Right? These last 2, both the penny and nickel are tails. Let's put H up over here. What does H say? H says calculate the probability the penny or the nickel are tails. Ooh, that word or. We're going to see that. Penny tails or nickel tails. What is the probability? Well, again, our denominator is 8 because that's our number in the sample space. So the penny being a tail is 1, 2, 3, 4. Or the nickel being a tail. So wait, I don't want to count those differently. I don't want to count them again, right? So it would be penny or nickel being tail. So let's see. Here, 1, 2, 3, 4, 5, 6. 6 out of 8, which is 3/4. Okay, so H is 6 out of 8 or 3/4. I says calculate the probability of no tails. Okay, well, that's just this one here. All heads. No tails is just 1 out of 8. J, where's J? Calculate the probability of either 0 or 1 or 2 or 3 heads. So here's 0 or 1 or 2 or 3 heads. Looks like all of them. So that is, 0, 1, 2, 3 heads. All of them are. 8 out of 8, which is 1. K. We have a K. Calculate the probability of 4 heads. Well, we're only rolling or flipping 3 coins. I don't have 4 heads. That can never happen in this experiment. So 0. Okay? Alright, so this concludes section 2. We've done all of these together. I will see you in the next video for section 3. Thank you for your attention.